People in here that have high GPAs that don't know that you have to, if you want to get federal grants for your graduate school career, you need to start applying now. All right? Now here's the deal. Most of my students that are American grad students, almost all, got either NSF, Department of Defense, DoD fellowships. One of them is a SMART fellowship. NASA has an Air Force, there's an Air Force fellowship, NASA has a fellowship. All of these are 3 years, no questions asked, money, $30,000 or $40,000 a year. They pay for, and you don't have to, there's no reports, nothing. It's for your research career. Professors love them. Problem is, you're not told about this in time a lot of times. So what I'm trying to do is tell you, you'll never regret a graduate education. You'll regret not getting it. And graduate school is not like undergrad. You're not taking all the courses all at once and you're just putting out fires. In graduate school, you really enjoy yourself, at least I did. Now, I went to Penn State, I didn't go here, but it's true, just about any land-grant university. You pick what you want, and you can sort of pick around, find something you really love, and then follow through with that. You'll not ever regret I've never met anybody that's regretted a graduate school career, getting a PhD or an MD or a legal degree or anything like that. There may be one case of an art history person that got a doctorate in that had a problem with employment. But as far as anything that's in the sciences, mathematics, engineering, medicine, you can't, if it's opportunities exist, do it. I'm going to tell you this. People say, I hate school and all this, you're tired of school. Don't worry about it. You'll love it. If you're good at what you're doing and enjoy some aspects of it, you hate some of the other things. I used to hate having to memorize all this stuff for all these other classes. I could care less about the gross national product of Brazil in 1947. But stuff like that used to just weigh me down because I didn't know it was really interesting. But when you're in grad school, the courses you take, you're really interested in, and it's a different world. I'm just leveling with you. So please, start looking at it now. Remember, National Science Foundation, NSF, DoD is Department of Defense, there's DOE, Department of Energy, there's NASA. All these are graduate fellowships. You have to be an American citizen, but you'll never regret it. And I'll write a letter for anybody that's doing it. It's in this class. All right, I want to get that out of the way. Check that box. What's next? All right, I gave you homework to do. It's basically the same homework, just to find. It's pretty straightforward. There's nothing tricky about it. I was going to show you, I put one MATLAB routine up there. I was going to give you the octave is the same thing. Do y'all see that too, class? All right. Just so you can confirm what you suspect. That's the only thing that's for. Right? And really the way you get it is always understanding the sine of n psi over 2 over sine of psi over 2. And that is the E field magnifier, you might say. It's how much better the E field's peak value becomes, or how the null's affected. Y'all follow me on that? Now the power would be n squared. And I'll talk about that one second. I'm just looking at, okay, it's time. We've covered everything in chapter 8. We're about to start chapter 9. Before I jump into chapter 9, I'm going to just say one or two things about chapter 8. And then I'll answer any questions you have. Is there more markers down there? Guess not. So, first thing is, remember, when you have an array, the total E field is always the E field from the individual element times the actual array factor that I'm talking about, where the array factor is simply equal to, and technically it has an E to the minus J n minus 1 over 2 psi, psi times the sine of n psi over 2 over the sine of psi over 2. almost always you worry about the magnitude. So this phase term goes away, and you're worried about the magnitude of that. That looks like a sinc function. I've said that several times. Y'all with me? Now, the other thing is, of course, psi itself is beta d cosine of the angle measured with respect to the rate of the actual axis of the array to the open angle plus some phase constant. In general, the way it's shown is there's going to be some number of elements out here, all spaced by d. And these will be in wavelengths. There'll be n elements, or yeah, n elements. There'll be a solid angle that's always measured, that's phi, from the axis of the array as it opens. We're assuming the magnitudes of the current will always be the same, and there'll be a progressive phase shift. All right, so they basically going to be a progressive phase shift there. Y'all with me, class? And that's the only thing you really have to understand. If you see this, you know the phase shift is the difference between the elements in the phase. Y'all follow me? It'll be progressive. The magnitude will always be the same. Now, that's the way it works for the antenna factor. I want to just show you one thing that I occasionally, I'm not going to give you this on this quiz. What?
Can you write down the equation that you usually get phi in that psi equation?
Well, remember the way we did it was we assumed this was R minus D cosine of phi, and what we did is got that infinite thing. You all remember? We had that or not? How many remember that? We had, I mean not an infinite series, but we had a closed form series, and then we got it down to 1 minus e to the j n psi, right, over 1 minus e to the j psi, and then I turned it into a sinc function, or a sine of n psi over 2 over n psi over 2. That's what this is. But this angle is this angle. That angle is implicit. It's not something I found. I defined it. Are you all with me on this, class? All right. It's just the angle. This is the array. This is the angle of the r vector to the array. So it could be 0, right? Or it could open up to 90 degrees, or it could be 180. Correct, class? Y'all follow me on this? I've defined that angle. I didn't, derive the angle. It's implicit to the geometry of the system. Okay, everyone? Now, here's the thing. When I look at this E field, this element, it could be a half-wave dipole, it could be a short dipole, it could be anything. All right, doesn't matter what it is. You have to know the direction and the main beam for this one is the main thing. That's the basic thing. This is just a whole bunch of numbers. It's just how many you have and the angle phi that feeds into that condition, okay? And that's it for getting this value here. And what I tell everybody when I'm doing these things, what you always do when you look at the E field plot the magnitude of E total. That's going to be the magnitude of the actual electric field, right, from an element, EL. I guess I could put M down there. And then it's times the magnitude of the antenna factor. Now, that's going to be the magnitude of the electric field. Y'all follow me? The magnitude of the antenna factor max will always be just n, the number of elements. Do y'all follow me on that? Everybody? This is important. Now, that means the greatest electric field enhancement you can have from a given element is going to be the element's electric field at that point times n. You all hear me? That's the maximum. All right, so the number of points, just take the number you have, multiply by n, and you get the E field enhancement. This is, or how much better it could be at the main beam. When you talk about power, this is for electric field. When you talk about power, all right, because power or average power, is proportional to the magnitude of E squared. Now, do y'all follow my rationale? I don't need to put the formulas down. I could put 1/2 magnitude of E squared over 2 eta. We could do it that way. We could find it from a single element and then find out what happens to array. But the real thing is this. How much greater will that E field be with the actual array? The greatest possible would be n times that, right? Therefore, the proportional increase in the power, P av max from the array, caused by the array, would be actually equal to n squared times P average max from an element. Are y'all with me on that? Now just keep this in mind. So it goes up, the power goes up by n squared. And it means one other thing to you, because remember when we calculate directivity, we take normalized power into account, don't we? Do you all remember directivity, the way we actually calculate it mathematically was 4 pi divided by the normalized power density integrated over the sphere, solid sphere, right? Over the surface of a sphere. Well, if the power density goes up by a factor of n squared, the value of the gain will go up by n squared as well. Do you all hear me on that one? So if you got a gain, just let me give you an example. If I have a short dipole, the maximum possible gain for a short dipole is 1.5. Do we agree on that? So if I had one element, that's it. I have a value of gain of 1.5. If I have 5 elements, I have 5 squared, or 25 times 1.5. Do y'all follow me on that? And that's why this directivity, I'm just trying to tell you, gain and directivity are proportional to n squared, not n. Now, think about this logically. Anybody here in the Navy? He's not here, the one guy now. Anybody been in the armed service at all? All right, yeah, you? Well, I've been on the Eisenhower. I was not a commissioned officer, enlisted, or anything like that. I've got a messed up hand. I can't get in the military. I couldn't even pay for my college. So, but I was a weapons consultant on the Eisenhower, and I was out to sea with it. And the one thing that you will see with the Aegis class cruisers around there are flat paneled arrays. They're not 1D, they're 2D arrays with about, I'm going to say, I'm just going to loosely ballpark it, 50 by 50 elements, all right? 50 times 50 squared would be the increase in the actual directivity from a single antenna there. Now those antennas are patch antennas. They probably have about 1.75, 1.8 dB of gain themselves. Well, actually gain, in dB is about 2 point something. But what I'm really getting at, that array basically is like a massive parabolic antenna. It's doing everything a parabolic could do. And I'm trying to tell you that the effect of, the multiplicative effect on the gain from arrays, rectangular arrays, is incredible. So that's what happens to the power. Now, a practical last example, just to show you this. If I was to give you this, and now please follow me on this. I'm not going to go fast. I want you to see this and appreciate it. Suppose I have 2 elements, but they're short dipoles. So these are short dipoles. And they're separated by B equals lambda over 2. Each one of these this has a current I naught. This has a current I naught e to the j 30 degrees. Everybody follow me on that? I could put it in radians. It could be pi over 6 radians, right? I'm preferred degrees at this point, just so you can appreciate it. 30 degrees isn't much. And in the plane of the board, where this is going to be a measurement for angle, now I want you to just listen to this. Here I'm going to say this is distance r, it's a long way off. This angle is theta. You all follow me on that? If it's a short dipole, we always measure the angle from the z-axis out to the radius vector, right? It's called theta. Y'all remember that, class? How many do? All right. For that, for the individual short dipoles, I know the E field, this would be the element, would be j theta beta I naught times L, the length, and I didn't put it down, make the length equal to lambda over 20, just for the heck of it, over 4 pi r, e to the minus j beta r, that's a phase term we could care less about, times the sine of theta, a theta. Y'all agree that that would be the electric field for one element, only one element, right? So we check that box, we can get that. I give you an I, you can get that. Y'all agree with that? Now, next, and here's where you pay real close attention, because here's where people mess it up on the final. And they mess this thing up routinely if you're not attentive, and this is an important class. Now, here's my axis of the array. Y'all agree it's horizontal? I haven't labeled it on purpose, because it doesn't have to be in the x direction, y or z. It can be in any direction. Do y'all follow me? It's just the axis where the array is laid on, you might say. It's the repetitive axis. Everybody follow me on that? Now, this is the angle that has to do with the array factor. Do you all see that? Right? How many do? You know where I'm going with this. These angles you can confuse very easily. But one angle in terms of the other, because this is a right angle, I can say what? That either I can put theta in terms of phi, and I could do that. I could say theta is equal to 90 degrees minus phi, or I could put phi in terms of theta, right? And that would be 90 degrees minus theta. Either one is acceptable. Or you could just put theta plus phi equals 90. But what I'm trying to say is one angle is defined by the other angle, and vice versa. Correct, class? Now, what I want to know is what the electric field will be like, the total electric field, in the plane of the board. Not in a plane perpendicular to it. Y'all follow me? Can you all see it? Did you have a question?
Is that 20 on the bottom?
Yeah.
9 over 20?
Yeah, I just picked it out of the air.
Alright.
Make it arbitrary, doesn't matter. I didn't give you value of current, probably I'd give you 1. What I'm trying to do is make this as easy as possible to see what I'm trying to show for. I'm going to come over here and do what I intended. So now, I'm going to do everything, and hear me, in terms of phi, the angle with respect to the array. You all hear me on that? You could do it with respect to theta, but then phi would have to be defined in terms of that. All right? So, with respect to phi, I know the electric field total would be equal to the element electric field, and I'm going to do magnitude so I can get rid of that j business and that e to the j beta r. So that's going to be eta beta I naught, and I'm going to leave it as L, over 4 pi r. Now it's going to be the sine of what? That's normally theta, but I'm going to do it in terms of phi. 90 minus phi. Do you all see that? Can you all see that? This?
That was me.
That was yours? This would have been theta, wouldn't it, class? But I'm going to do everything in terms of phi. So this would be, I'll get to this in a second, minus phi, right? Now I multiply it by the array. And I'm getting rid of the phase. I care about magnitude. So now this is going to become the sine of n psi over 2. Well, n is 2, right? Y'all agree with that? So 2 over 2 is simply 1, so it's psi, and psi is beta d. I'm going to leave it as beta d cosine of phi plus alpha. Now alpha is 30 degrees. I'm kind of mixing and matching things. Over the sine of n psi over 2, or beta d cosine of phi plus 30 degrees over 2. Right? Y'all follow me? I've literally replaced the psi with beta d cosine of phi. You follow me? All right. Plus alpha. Do y'all follow me? The only difference between this argument and this argument is that 2. But n is 2, and that's the reason it doesn't appear upstairs. Y'all follow me? How many see this right here? Now, that right there that's a statement, that for sure you can get. This, I'm going to tell you, sine of 90 minus phi could be the cosine of phi also. If you just look here, isn't the sine of this angle really the cosine of this angle? Can you all help me see that? Right? So I could, to make my life a little simpler, let me just make this cosine. You don't have to do it. So now I have that, okay? And I'm going to do something. I'm going to put magnitude here. So now what does this look like, right? Now I replace, you can plot it on a computer very easily, right? You all agree with that? But if you had to estimate what it would look like, and I'm going to go over here to do this. First, you all see what I've done and why I've done it. All right. Now, over here, what I'm going to do, actually, I need to erase that right there, and I'll do it there. So now, when I take a look at the element itself, what it looks like, the element pattern, well, this particular dipole would have a pattern like this. And I'm being consistent where this axis, whatever you label it, you could label it X if you want. This would be the X-axis here. Y'all follow me? Y'all agree that would be the pattern for a short dipole, correct, class? It would be about the same for halfway. The peak value would be 3/2, and it would look like that. It would be a sine function, correct? Or cosine if the measurements are from the X-axis, correct, class? Now on top of that, that pattern would be multiplied by the pattern of the array, right? Correct? And do you remember what you're doing with the pattern of the array to do it? You're taking actually what? The sine of n sine over 2 over the sine of psi over 2. And where is the maximum on that one? In terms of psi, people? I'm doing this for your benefit. How do you always get that? Where is it?
Psi equals 0.
Psi is 0, right? It's like a sinc function when the argument is 0. So psi equals 0 is the max. And in my case, for this one, right, psi itself is beta, which is 2 pi over lambda, times the separation distance, which is lambda over 2, right? Then it's times the cosine of phi, that phi. Agree, class? And it's plus alpha. What's alpha again?
30 degrees.
Yeah, and I'm going to put it in radians here. That would be pi over 6 radians. Agree?
Yeah.
Now, I'm just doing this for your benefit. To be a maximum, that equals 0. Y'all follow me? So when it's equal to 0, and I'm just going to put this below, for the max, when this is 0 here, I better do it right here. I have 0 is equal to pi cosine of phi plus pi over 6, right? That's equal to 0. You all see I can get rid of that pi in a heartbeat. Agree, class? I'm going to do that. Next, what am I going to do? Take the 1/6 to the other side. Correct, class? That's minus 1/6. The solution to that is the angle where the maximum occurs. Do y'all follow me? Can somebody give that to me just out of curiosity?
99.6 degrees.
All right, that's a bad angle. So down here, I'm drawing it, 99.6 degrees is here, right? I know there's a max here. Where's the min? Where's the first min going to be on this? How did I always tell you to get it? Anyway. The first minimum is when this sine function is 0
So-
after 0. Huh?
So is it positive pi?
It's pi, isn't it, class? Remember, when you look at this argument, If it's 0, it's gonna be a value of 0, but I have 0 over 0, so with L'Hopital's rule, you get a relative maximum, right? You get a value then. Then the first 0 after that, for the sine function, is when this, n sine over 2 is equal to pi. Y'all follow me? And you can put plus or minus pi. It's a symmetric pattern. So when it's equal to pi, that means 2 pi over n would be psi. Isn't that right? Y'all see this? If you have n psi, right, over 2 equal to plus or minus pi, I'm going to take the plus, just to simplify my life. It'll be symmetric. I get this. So then I multiply both sides by 2. Do y'all follow me what I'm doing? I'm just solving for psi here, correct? So then this is multiplied by 2 divided by n, and this is the value of psi for the min, right? And this is the first min. Y'all follow me on that? Now n, can you see it okay? N is 2, is it not, class? So it's just equal to what? Pi. I'm running out of room, I'll do it here. So psi is equal to pi is equal to beta d, which is what? Pi times cosine of phi plus pi over 6. Do y'all follow me? How many see what I'm doing here? This is the homework stuff, but I'm just doing it one time in class so you can see this, and then we're going to multiply the patterns in 1 second. Now, when you get that, what happens? Y'all agree I can divide by pi on both sides? So I get a 1 there, and this becomes 1/6, right? And then I subtract 1/6 from both sides, or take 1/6 from both sides, get rid of that, and this is 5/6, right? Can you tell me what the value of phi is that solves that? Now remember, this is only the positive one, but just do it.
33.56.
Anybody confirm that?
Yeah.
33.56. That's the first min. So remember, phi is measured from the x-axis, so it's about there. Well, that's a little high. About there. Now these patterns are going to be symmetric about this axis. Do y'all follow me? Now look at that. That's the min. There's something out here we don't know. It's actually relative. We hit something like this. And then it's going to go like this. Something like that. Y'all follow me on that? Now when I multiply this times this, what do you get? Here's what you look for. You look at the nulls. The nulls on this one are straight up. Do y'all see that? That null will override. When you multiply these two patterns, there's going to be a relative null here going straight up and straight down. Do y'all follow me? These are supposed to be symmetric. My drawing is not symmetric, but I hope you can appreciate somewhat what I'm trying to do. It'll be symmetric about this axis. However it opens this way, it'll open that way the same. So there's going to be a null here, I know that. Then there'll be a null here and a null here. So when you're done, all this, what I'm going to say, it's going to look like this. And this is not drawn real well. Wasn't the best example, but now you're going to get something where this starts coming up, goes back to a null, and then right over here has kind of a relative maximum, kind of a relative maximum. Over here it comes out, and that will be the pattern. It's not drawn really. I wouldn't expect you to be able to draw that to scale, but you should at least be able to show a relative sketch of the E field from the actual antenna element, and then from the actual array factor, and just kind of gross estimate what it's going to look like. I don't expect anything precise, okay? I don't make them hard. I would pick better values, but I'm trying to show you that. Now, give me 1 second on this. What I showed you is the way to do it for this particular thing, right? If I asked you, go ahead. Did you have a question? Okay. If I asked you about the power pattern, hear me now. Once you have this pattern, you probably do it with a computer, you just square that pattern's value. Whatever you use to drive this pattern, take that magnitude and square it, and that will be the power pattern. Do y'all hear me? That'll be the norm, and always normalize it to the maximum value of 1, 2. Okay, now, question?
Oh, I figured it out, sorry.
Question? Yeah.
So on the homework, when we did max and mins, I'm just relating it to this. We got, like max and mins of 0 and 180 when we solved for other values. How do you get those?
Well,
values?
remember what I said about how the pattern repeats itself if this spacing is greater than lambda over 2? Remember that, people? If you have the separation distance greater than lambda over 2, the pattern as you start from phi equals 0 up to some max will just repeat itself because there's an ambiguity. There will be two angles actually where the same constructive or destructive interference will occur if the separation distance is greater than d over 2. Did you follow me on that one? Now, I'm not here to confuse you on this. So, just for the record, I won't do that. But he did. He gave you what, 5/8 lambda, the separation distance? He did that on purpose, so to make you look at more than one minimum and maximum. And that's just where the pattern repeats itself. When you take antennas, if you do, you'll see all this. This is a little further down the road. Remember?
So are you saying like if it were,
5/8 lambda.
yeah, so
Then most of the patterns, that you would get a pattern from 0 phi equals 0 up to some maximum value. It might, I'm not sure what the angle would be. And then at that point, the entire pattern repeats itself from the 0 point. It's like, that would be a full period, all right?
you would add 180 to that?
Then basically it would start there and just start going again. And I promise you, a lot of this stuff gets kind of hairy and deep, but you should at least appreciate, if you want to have full field of view from 0 to 180 degrees, don't ever space these individual elements by more than lambda over 2. That is the golden rule when you do these things. Now, if you have a very limited viewing angle, then you can separate them greater if you don't care about doing a full scan. But otherwise, you have to have a separation, maximum separation distance, a lambda over 2. That's what I wanted to say in recap of what we were talking about. And you did the problems, so you're in good shape if you've done those problems. Now, next, I got a few minutes. I just want to tell you what we're about to do. We're going through EMs, we're really going through electromagnetic interference and compatibility, which is a huge problem these days. I want to say one other thing about compatibility and interference. With the advent of all these autonomous vehicles, autonomous cars, I'm not sure if all Teslas that are out there have the ability to self-drive, but some do. How many know that? How many know that there are cars you don't have to drive? There's a guy that drives to Archangel, where my wife works, from Atlanta every day with a Tesla. He's doing other stuff. He is not driving. His car is using sort of an artificial intelligence type of navigational system. Now, in fairness, this stuff is pretty well tested. They're using GPS location, they're using all sorts of stuff, and they have radar, collision avoidance radar. They've got a bunch of things. However, the problem is always this: non-compliant vehicles and UAVs. By that I mean, what if you have somebody who's putting out a signal that overwhelms their radar, or it's something that basically is interfering with the operation of that vehicle? It's much worse in the air, and that does happen. All these vehicles rely on sensors that interact with the environment as well as either GPS satellites or cell phone towers, or both. And the minute something external that's not supposed to be there starts interacting with them, it can be intentional and spoof that thing. How many know what spoofing is? You heard the term? That's what happens to drones when you want to get them. You make them think they're somewhere they're not and land themselves in bad places. That's what happened to one of ours over Iran. Well, you can spoof cars too. All this stuff is, the reason it's safe so far is most people aren't, we don't have state agents trying to wreck Teslas on a regular basis. And we don't have them trying to steal Teslas. As a matter of fact, there's encryption involved, and it's a fairly complicated thing. But if some clever people wanted to, they could do it fairly easily. Encryption is something that's great until you get a real clever person that's not so great. All that stuff can be, anything created by man can be broken by man. And so interference and electromagnetic interference The first thing when you do all this stuff, you have to understand is how the signal could actually get in there. And that's what we study next. And I have a great interest in this for other reasons, because I have been around some of this stuff where people use different means of doing things. For instance, most of you, when you think about, I guess, electronic warfare or jamming or spoofing, you think about radiated emissions through the air doing it, right? See that plug right there? There are two conducting tubes that basically go throughout the building. That is the perfect waveguide / transmission line, where you can get a very easy path right into the system because it goes through a rectifying circuit. Usually it's a full wave rectifying circuit, and it's very easy to penetrate a lot of systems that are plugged into a wall. I'm giving you as a heads up. All right? There's things that I've encountered that I didn't expect. I thought that was easy to shield. It's far from easy. So here we go again. So this is going to be chapter 9. And this is going to be EMI, electromagnetic interference, electromagnetic compatibility, and I'm going to go a step further, call it FCC, Federal Communications Commission Management. We're going to go through the 9 yards of this, the whole 9 yards. So first with EMI, the key thing to begin with is knowing what components look like at different frequencies. And we start with the most basic, which is a wire. Now, when we talk about a wire, at least for electrical engineers, they're mainly copper, highly conducting, and they're round. They don't have to be that. They can be all sorts of shapes. They can be flat, like if it was on a PC. Any kind of conformally mapped circuit usually has flat lines. But we start with a wire because it's fairly obvious and easy to work with. When we deal with a wire, the first thing we talk about is the resistance of a wire. And if you have a wire of length L, and it has a conductivity sigma, and again, these are standard things, and it has a radius A, then it is a constant cross-section transmission line component. Do you all agree with that? So the standard way of getting the DC resistance, or DC for that, it's always proportional to the length of the wire. It's inversely proportional to sigma, which is the conductivity of the material, copper usually. Very high, about 5.8 times 10 to the 7th, and that's 1 over all meters. Then it's also times the cross-sectional area A, and for a round wire, it would be pi A squared. You all agree with that? So that's the DC resistance of a wire. But that's not usually what we care about. We care about the AC resistance. We talked about skin depth. You all remember that? So now, that's DC. When we talk about AC resistance, now we calculate the skin depth first. And it's going to be 1 over the square root of pi f mu sigma. The sigma and the mu would be of the wire. And we make an appropriate statement that if the skin depth is less, and let's go much less than the radius, A, then our high frequency, and I'll call it, I think in Whitworth's book he calls it AC, but I'm going to call it HF for high frequency, would be still equal to L over sigma. But now remember, the area is severely reduced because now the area, the cross-sectional area the current flows through is simply 1 skin depth thick right there, where this is the outer radius A. And therefore that area becomes 2 pi times the skin depth times A. Do you all remember that, class, where I got it? Here's what I do normally to do it. I say just cut it right here, or cut it in one place, up there, and then unravel it. So you would have something like this. You would have something that's as long as the perimeter, or 2 pi A long, and the thickness would be a skin depth. You all follow me? That's how I always think about it. That would be the cross-sectional area the current's flowing through. You all with me? And the higher the frequency, the smaller the skin depth gets, and the smaller that area gets. So that, and these are ohms. That's the first thing. The next thing is gonna be the inductance of the wire, but it would be internal inductance. I think I gave you the talk about why we can't talk about total inductance of a wire. Does anybody remember that? You remember me talking about internal inductance? How many do? How many remember skin depth? Okay, it was during those lectures, but if you don't, I'm gonna go through them again. Anyway, you all know when I talk about internal inductance, it's like internal anything, it's inside the wire. The magnetic energy stored inside the wire is associated with an inductive value, an inductance, all right? When you do internal inductance, L, DC, there's a very interesting thing about this. Does anybody remember what it is for internal inductance of a wire? It's not a function of the geometry. It's always what? Mu over 8 pi times L, the length. Mu over 8 pi doesn't matter about the radius. Does anybody remember that? Well, it's in henries. Now, if you wanted it per meter, you get rid of L. Y'all follow me? This is henries. You can look this up. This is interesting. That's internal inductance, DC. But for AC, it goes down. And then L, and I call it high frequency, is equal to this, LDC. This is the way I do it. And then it's going to be 2 times the skin depth over the radius A. Now, in Whitmore's book, this is equation 9.6. He doesn't have it the way I do, but I like using this over and over again for one reason. Because I know that formula very well. It's stable in my, so I'll just use this, do the multiplier, 2 times the skin depth divided by radius A, and that's it. But you can use his formula, they're the same, all right, for the thing. And that's where I stop this lecture. I'm going to start next time. We're going to cover what components look like and everything. And then ultimately how the signal gets in, what you can do to prevent it if you're lucky. Okay, could you do me a favor? Let's see. How about leave this row populated where you are? Empty that row. Leave this row populated. Empty that row.